Every episode of this series has looked at one part of what happens when you use Postgres. This one puts them together, one query traced end to end, with every part of the machine we've talked about doing its actual job in real time. Start when the SQL text arrives at Postgres. First, parsing. The text is turned into a structured tree. Column names are looked up, syntax validated, table names resolved to on-disk objects. Cheap, rarely the problem, but the point where Postgres tells you your SQL is malformed rather than trying to run it. Then the planner from episode 3 takes that tree and turns it into an execution plan, choosing scan types, join methods, join order, all based on the statistics we spent a whole episode on. This step is where a query that ran fine yesterday can quietly go wrong today. Same tree in, different plan out, because the statistics changed. Explain-analysis-buffers shows you what the planner produced. Then the executor actually runs the plan, node by node, reads from tables, walks indexes, performs joins. Every read the executor asks for goes through the buffer cache, a chunk of Postgres's memory holding pages recently read from disk. If the page is there, the read is fast, a few microseconds. If it isn't, Postgres has to fetch it from storage, which is orders of magnitude slower. Explain-analysis-buffers shows you which is happening. If the query only reads data, that's most of the story. If it modifies data, insert, update, delete, one more piece of machinery kicks in that most people never hear about, but that every production Postgres depends on, the write-ahead log, or WOW. Here's the fact behind it. When you commit a change, Postgres does not write the changed table page back to disk right away. Writing pages to their final location on disk is expensive and involves scattered random writes. Instead, it appends a compact record of what changed to a single sequential log file, the WAL, and calls that committed. The change is now durable because that log write is real. The actual table page in memory gets updated too, but its trip back to disk happens later, in batches, by a background process. If Postgres crashes before those pages made it to disk, the WAL replays on restart and reconstructs exactly what was committed. To make that efficient, Postgres keeps table pages in memory as long as possible and keeps some estimate of how much it costs to read each page in ambitiously named goodness counters. So, one query has parsed, planned, executed against a mix of memory and disk, and if it wrote anything, its changes are safely in the log. The response goes back over the connection. Which brings us to the last piece and the honest close of the whole series. Every connection to Postgres is a full operating system process, not a lightweight thread, an actual process with its own memory, scheduling, overhead. 10 connections is 10 processes. 1,000 is where Postgres spends more effort context switching than actually running queries. It doesn't matter if most are idle. An idle process still occupies memory and counts against OS limits. The reflex when you hit connection limits is to raise max connections. Almost always wrong. You're not adding capacity, you're adding overhead, and making the moment your database falls over come sooner. The actual fix is a connection pooler, a small proxy like PgBouncer sitting between your application and Postgres. Your app opens as many connections to the pooler as it wants. The pooler holds a small, fixed number of real connections and multiplexes queries across them. 1,000 app connections become 20 database connections, and Postgres goes back to being fast. Connection pooling isn't optional at any real scale. Every production Postgres over a modest size has a pooler in front of it, and just increase max connections is one of the most reliable ways to make a small problem into a large one. Now the honest close, because a series that only sold you Postgres would be a sales pitch. Postgres is an extraordinarily capable engine. It will happily let you push it further than it can hold up. And the last skill this series can teach you is knowing when the answer isn't Postgres at all. If your workload is dominated by simple reads of the same rows over and over, a cache in front of the database, Redis, Memcached, anything, will absorb 90+% of that traffic and leave Postgres for the actual work. If reads massively outnumber writes, and the reads can tolerate being slightly stale, a read replica, a copy of Postgres, kept in sync via the wall from earlier in this episode, lets you scale reads by adding machines rather than by asking one machine to do more. If you're using the database as a work queue, polling a table for pending jobs, marking them done, you're going to lose that fight against a real queue like Kafka or SQS, no matter how well you tune. And if you're storing time series data and asking analytical questions across billions of rows, a purpose-built store will outperform Postgres by orders of magnitude, not percents. None of that is a failure of Postgres. It's a recognition that database isn't one thing, and different shapes of work fit different tools. The best Postgres users know exactly what they use Postgres for and exactly what they don't. Pull the whole series together. Postgres stores data by never overwriting anything, which is why bloat and auto-vacuum are the shape of half of its operational reality. Indexes are secondary structures that make reads faster and every write slower. The planner turns your SQL into a real choice between alternatives, and its estimates depend on statistics that can go stale silently. Explain Analyze shows you the plan against reality, and rows planned versus actual is the number that matters most. MVCC gives you consistent reads, locks give you correct decisions when contention appears, and the machinery underneath, buffer cache, wall, one process per connection, is what determines how far a single Postgres can carry a workload. Postgres does not fail when it's slow. It tells you what happened. Explain tells you what it decided. PgStatActivity tells you what it's doing right now. PgStatUserIndexes tells you what's earning its keep. The whole system is inspectable, and the operators who look good in production are the ones who look at those outputs rather than guess at configs. That was the argument the funnel opened with, and it's the note the series ends on.